Welcome all of you this last class in river engineering course, and today we will talk about physical river models. Okay, basically the experimental works, what is necessary to do, understand the flow process, sediment process in rivers. So, it is a scale down models. So, to start that I'll tell it that regarding the physical river models, we should have a knowledge on dimensions and similitudes. That is what I have covered in fluid mechanics, which is a mock course is available. So, please go through that 2 lectures on dimensions and similitudes. That some component of that I will cover it here, but more details of dimensional analysis and the similitudes you can follow the mock course on the fluid mechanics designed by me. So, you can look at that, and more or less we are following river mechanics P.Y. Julian book, and that is the physical river modeling concept what we will discuss it. And since it is a last class, anyway I am not going to more details of physical river models, but I will try to develop a confidence on you how to model physical models for a river reach. So, if you look at that, I will show some case study of river physical models used for Indian rivers, and then I will talk about the different type of similitudes. As you know from basic similitudes like geometric similitudes, kinematic similitudes and the dynamic similitudes. And here we talk about 2 types of models: rigid bed models, mobile bed river models. So, you can understand it, one case the sediment transport is dominated. So, that is what is the physical river models, and we can have a rigid bed models where the sedimentary process is not that dominated. So, that case we can use the rigid bed models. So, we can divide into 2 parts. Okay. One is exact Proud similitudes, another for the tilted river models. Similar way, the mobile bed models will be complete incomplete models. I am not discussing much details here in complete models. We will just discuss about complete mobile bed similitude. Before trying these things, to develop a river physical models, we should have enough knowledge on river engineering. That knowledge will be helpful to establish a appropriate river physical models, and what is our objectives, that we should try to understand it engineering point of view. It is also a knowledge, the art of modelings, we should follow it to have a appropriate model for a river problems. Now, if you look at that very interesting lab setups what we have, and there we are trying to set up a small set of river model for Brahmaputra rivers. If you can look at the river Brahmaputras, okay, if you look at this braided loop and the flow incoming and outgoings, the same concept when you talk about, if you look at this is what the prototype level, which is showing the satellite imagery, and we are developing physical models, okay, which in the lab scale is a scale down models. It is a scale down models, and with a training work we can see that there are geotubes are there, which are the training works. Before implementing the geotubes, we can know it, what is the impact of the geotubes on river morphology. That is what we conducted a study and try to look at how the geotubes are effective for arresting the bank erosions. So, if you look at that concepts, and what we have done it, that particle size of the D50 of the prototypes, this is the prototype, this is the models is the same. The river discharge is a 10,000 per meter cube per second. We put a model is 10 liter per second. The river length of the island is 6 kilometers. In the model scale is 1.73 meters. Okay. Width of the island is 2.5 kilometers. At the model level is 0.72 meters. Now, if you look at the width of the right channels, width of the left channels, that is what we have in there. So, this is a scale down model. So, if you look at that, geometry scale down models is there, as well as the discharge, the scale down is there from 10,000 meter cube per second to 10 liter per second, and it's a mobile bed condition. It's also mobile bed conditions where the sediment, the bed load sediment process are happening it. That is what you can see it. Okay. So, we always have a scale down models from river to the laboratory scales. That is the scale down models. Today we will discuss it, how to develop a scale down models. Okay. That what we will discuss more details. Now, if you look at the similar one examples, I will take it that physical river model study for a bridge in Brahmaputra rivers. That means, this is the bridge proposed to be constructed. The same models of the bridge and the piers, you can see it. That is what is done it on a physical model setups. Okay. So, this is the proposed road bridge on the Brahmaputra rivers. The same things what if you look at, it is implement in physical models. Okay. And these dots are representing bridge piers. Okay. Representing bridge piers, and this is what the man channels and other channel formations are also there. So, this is the prototype, this is the prototype, and this is the models. Now, let us look at what is the scale down it happened it. Here the design discharge is 99,000 meter cube per second, which is close to 100-year return period flood. Horizontal scale is 1:575. The vertical scale is 1:65. River width 15 kilometers. The basic idea to know it, discharge intensity variations, upstream afflux due to the bridge. So, if you look at that, we before implementing a bridge projects, we do a physical river models to know it, how much of discharge intensity variations are there, how much of scour formations will be there at different bridge piers, what could be the upstream afflux will be there because of this construction of this bridge. So, this type of the prototype to models we do it in the laboratory to know it, the flow and sediment transport processes, what is happening at the model scale, and that basis we predict it what could be the scenario in real river conditions. That is what we do a scale down models. We remember here we have used the horizontal scale and vertical scales are the different. That means, is a distorted models. This is what distorted models. We are the horizontal scales and vertical scales are the different. Why we do follow basically the different distorted models? For example, if you look at these rivers, as it can see that the length of these rivers can be in terms of 100 kilometers. Okay. Width is 15 kilometers and the depth of the flow maximum will be the 30 meter. That means, it is a kilometer orders in the platform dimensions. One is 100 kilometers, another is 15 kilometers, but depth when you talk about 30 meters. If it is that the scale, we cannot use a geometric similarity models, exact models, because we cannot represent the same scale in the vertical direction and the horizontal direction because of the river dimension. That is what many of the times we talk about the scale issues, okay, because the scale, the dimensions of the river in terms of length, width and depth, that is what is very considerable. So, we need to have a distorted models. That means, we will have a vertical scale and the horizontal scales are the different. Mostly the vertical scales are the finer scale, then the horizontal scales will be the coarser scale. Now, if you look at 3 dimensional models, which is a CWPRS Pune, okay, Central Water Power Research Stations in Pune. If you look at that, this is what the Kosi barrage, you can see this Kosi barrage and abatement, all it's at there. So, it's try to know it how this flow is varying it, okay, that is what is at the physical models levels. Okay. The same way, if you look at this Kosi rivers, where we lot of study has been done for the Kosi barrage, like putting the different type of river training works, what is the effectiveness of river training works to protect the river banks, and this is what the river flowing. So, if you look at that, we conduct a series of physical based models for the Kosi barrage as well as Kosi rivers. Same way, when you talk about hydraulic structures like a Indra Sagar Dam, a 3D models we prepare it exactly, a scale down 3D models. Pungat 2 3D models. Okay. Similar way, this is the port and this is the backwater at Pumpara embankments. So, if you look at that way, always we conduct a physical river models to try to understand it at the structure, how the flow process are happening it. Okay. This is a 3 dimensional models. These are 2 dimensional models representing the plant forms, river training, how we have to have a river trainings, and you also have a backwater for these conditions. So, we do the physical river models. Central Water Power Research Stations Pune is leading in our country to do physical river models. Now, if you look at that, how you do the hydraulic similitudes. That means, we have a prototype, we have the models. We try to do a scale downs. That is the reasons prototypes conditions which we give a subscript of the P is a full scale conditions, okay, field conditions. M is in the hydraulic models conditions is built in the laboratory. The ratio between the model scale, the ratio between the model to prototypes. That means, what we do it, if any parameters like a length by prototypes by the length of models, that what will give length ratio, length by prototype by the length of models will give us the length ratio. So, we define in the scale on this, we define this the scale of this by this length of prototype by the length of m. So, if you look at that, most of the cases we do the studies on the earth. So, considering that, if you look at the gravitational accelerations of the prototypes and models, the Gp and Gms, they are equals. Okay. That is the reasons the scale ratio for the gravitational accelerator fluid, it comes out to be 1. So, if we are using the same fluids, okay, same water or same liquid, whatever is there, the same liquids you are doing any physical models. So, the basic proposition like a density ratio, acceleration due to gravity ratio, dynamic viscosity, kinematic viscosity, unit weight ratio all becomes 1. Okay. So, the condition is that we are using the same fluid. Okay. So, you are using the same fluid. So, then our model ratios will be the same. The most of the times, as I said it, we cannot do a total geometric similarity models, because we have a lot of constraint like the length, okay, the physical limitations in terms of the space, water distance, instruments and accuracy, how accurate instruments we have to measure the velocity, measure the flow depth, measure the turbulence properties, measure the sediment. So, what is accuracy? That also is matters to design the scale. The scale does not mean it that we can do very finer scale unless otherwise you have a highly accurate instrumentations with us. So, similar way we should implement the boundary conditions, okay, upstream and downstreams like these flow models. If you look at the proposed road bridge, this is the bridge structures and this is the guide bond, okay, and you can see that how the flow things will happen. So, in this case we need to know it what could be the upstream conditions, what could be the boundary conditions. When you develop the physical models, these two conditions also should be satisfied. Now, if you look at what you are doing it, as I said it, the vertical scales ZR directions. So, basically what you have any models you put it, okay, in a 3 dimensions, okay, you have a XR, you have a ZR which is vertical directions, and we have the OAR. So, most of the times we try to look at whether you want to do a 3 dimensional models, okay, then you need to look at all these components ZR, YR, XR. Okay. The Z is vertical ratio, Y is a lateral ratio, XR is the longitudinal ratio, longitudinal length ratio, the ratio of the longitudinal directions. When you do exact geometric simulations, okay, that means your vertical length scale is equal to the horizontal length scales. That means your XR is equal to YR equal to ZR, okay, which can be done it for a smaller stretch. Okay, it is exact simulations. Okay, similitudes. That means you are not distorting it. Okay, you are not talking about like a 3D models of a hydraulic structure, like a dam structure. We can have all these conditions satisfied. Okay, so the ratios can be also satisfy XR, YR, and ZR. And this is the conditions when you have, that is the length ratio, that called geometric simulators. We call geometric simulators. But many of the times, as I said it, the vertical scale of the rivers are much lesser, vertical depth of the rivers are much lesser as compared to width or in compared to the length. So, we do the vertical scales different than the lateral scales. In that case, we have a model distortions. Model distortions we have in that when the vertical scales are not equal to the horizontal scales. The distortions factors were minus by the ZR, okay. That length ratio in the YR directions by ZR is a ratio in vertical directions. So, vertical scale is not equal to Z square. In this is the case, if you want to estimate the flow area, in case of exact geometric simulations, area will be the square of the length, okay, the square of the length ratio. The volume will be the cube of the length ratio, but that is what will be substituted. In case of volume, you have XR, YR, ZR product of this. The horizontal surface and the cross section surface will, you can interpret it will be like this. So, the basically when you use a distorted models, you use XR, YR, ZRs are the different. Otherwise, if you have a exact simulation models, you use the LR. So, for that area will be the LR squares and the volume will be the LR cube. But in case of when you are using XR, YR, ZRs are the different in a distorted models, then your area will be different depending upon whether it is a horizontal surface or the curved sectional surface. In horizontal surface, you will have XR and YR, and in the cross section surface, you will have a ZR, YR. The volume will be the XR, YR, ZR. So, please give attention to this, which is a ratios. Okay. And now, if you look at basic next similitude is called kinematic similitude, as we discussed in dimensional and similitude analysis and similitude analysis in fluid mechanics. So, the same concept. That means, is this just we are taking an example, the flow past a cylinders. Okay. This is the original cylinders, or the you can say is a bridge piers, and the flow is coming it, which is a cylindrical shape. This is the prototype levels, how the streamlines are happening, how the velocity distributions are happening it. The same geometry kinematic similarity we have to do it, the scale down this the diameter of the bridge piers, which is a cylindrical bridge piers, to this shape, and then we can have a scale for velocity components, and so that the streamline patterns, the velocity ratio, that is what will be maintained it. The length ratio, the time ratio, and the velocity ratio, whatever is there, that what can maintain it. So, if you look at that part, that means we are introducing whenever kinematic centimeter, that the parameter involving length and time, that is velocity, accelerations, and kinematic viscosity. Okay, that's also will have the same VR we are given as a Vp by Bf, prototype by the models. So, you have a TR will be the time scales, will be ratio of the time scale, it will be Tp by Tm. If you look at that, and basic properties, as you know it, the velocity is equal to length by time, and you know it, velocity divided by the time will be the accelerations. So, if you use these two terms, okay, and try to look at the velocity and the length ratios as we deduct that part, and the accelerations as we can consider is 1. Okay. So, in that case we will get it, the V r by Z r 0.5 is equal to 1, which is the flow proud numbers, B square by rho G H is a constant, that is what you know it. So, when you do this kinematic similarity, it needs to have the proud similitudes criteria. So, even if that is what is hold good it, that is what is indicating here, that you will have to have that conditions. So, once this is the conditions is there, the proud similitude criteria is there, you can compute it time scales as well as the velocity scales. Now, we can go for the distorted models, where the time scales varies along the directions. The restricted to simulations 1D flow, it cannot account for the 2-dimensional 3 convective and turbulence accelerations. Okay. When you do the distorted model or tilted model, so it is not used to model the vorticity, diffusion, turbulent mixings, and the dispersions process. These distorted model you can use it, and most of the times when you talk about the reverse scales, we have to use distorted models. Now, if you look at the dynamic similitudes, that means we are talking about, as if you look at the prototype of models, okay, it is a scale down models. So, all the gates are also scaled down, flow properties are scaled down such a way that if I take a points which is having the force because of inertia, the gravity force, friction force, and the pressure force, and force diagrams like this. The force diagrams will be this more or less the same. Okay. The force diagrams will be the more or less the same, but only the magnitudes will be different. When you attain that, then we call dynamic similitudes. Then we call the dynamic simulations at that what its conditions happens it. That means it is involving with a mass, okay, that means mass density, specific weight, dynamic viscosity. When we try to have the ratio between the model and prototypes. So, that is what is the ratio of the densities and these mass ratios what is there. So, individual force acting on corresponding fluid element must have the same force ratio in both the systems. Okay. Both the systems they have the same force ratio, exact similitude of all ports in hydraulic structures is impossible, only at the full scales. So, when you look at to have exact similitudes, that means the geometric similitude should be satisfied, kinematic similitude should be satisfied, and the dynamic simulation should be satisfied. If these three conditions is satisfied, looking all these equations, we can know it is only the possibles when you have a full conditions, which you cannot implement. The river, the scale model, you cannot implement the full scale model for a rivers, it is impossible. So, we go for distorting forces. How do we get it? We look at which are the forces negligibles, like whether the friction force is dominated, whether the inertia force is dominated, the gravity force or the pressure force. So, based on that, we try to look at which is the dominated forces, like most of the open channel flow, the gravity plays the major roles. Okay. So, we try to look at the gravity is more impact when you have the open channel flow, or you look at where the viscosity or the flow resistance play the major roles. That is way we try to look at which component of force we can use for the prototype models, which will be show the dominated forces. Other in not a negligible forces like other components, always we can neglect it. That is the strategy being followed for river physical models. Now, let us come to the rigid bed models. Okay. Rigid bed models, when you consider it, like you have a hydraulic structures, okay, spillway, you have fish ladder passes, okay, where the sediment transport is not that significant, or you are not considering the sediment part that extensively. We are looking more towards the flow structures. We try to more towards to understanding how the turbulence behaviors are happening, not considering the sediment part. So, we can go for rigid bed models, which is a fixed bed, okay, as name implies, the no sediment transport. That is what we consider it when the silt parameters is less than 0.03. Okay. So, you can see a river flow where you have the silt parameter is lesser than 0.03, then you can consider it is rigid bed model. Okay. Rigid bed models. So, basically what we try to look at, resistance flow should be the same for model as well as the prototypes. So, it needs to have a exact geometric simulations, that means resistance flow can be neglected, or you can have a distorted and tilted models where a resistance flow is important. That is what you have to consider. Exact geometric similitude and proud number similitudes, okay, can be simultaneously maintained when the resistance to flow can be neglected. So, you have a geometric similitudes, you have the proud number similitudes, that is what we can maintain it. It is possible to do it only if the resistance to the flow can be neglected. Okay. So, basically it is itself for the three dimensional flow around the flow structures where the sediment is not river, but when you the long river reaches like a Brahmaputra or river where flow resistance play the major force components, okay, we cannot neglect it. In that times we should do the proud number similitudes as well as resistance similitudes, which basically the Manning's equations or the Stickler's Manning's equations, we can use it to satisfy the for tilted and distorted models. Okay. Now, if you look at that exact proud number similitudes, as already have discussed, is that we try to look at first the exact geometric similitude should be there for the proud similitude criteria, and it is what 3 dimensionals. Okay. If the vertical allocations are not negligibles, that is what you need to have a 2 dimensional models, and these are the particular well suited model for flow near the hydraulic structures, as I said that spillway structures or sluice structures. So, all these and you can have the length scale and the mass scales like this. Okay. You have a length, the time and the mass scales using the fundamental dimensions we can consider it and we can derive it. Okay. I do encourage you to follow dimensional analysis at similitudes in fluid mechanics courses to know it, how to get it. The mass ratio is a function of the length ratio or the that is what you have to do it by considering these dimensions of the variables. Now, if you look at there is a two conditions again is coming it, that exact simulated imposes constraint that is usually difficult to work for modeling of the rivers. Scaling the size of roughness also it matters it. Okay. So, when you do a river models, what is the size of roughness you will get it. Okay. This is river, okay, which is the your prototype. Okay. And you have a scale models, okay, which will be the few centimeters and you have in terms of meter, 10 meters. So, the you need to try to look at the resistance what you are saying it are the same orders. Okay. So, if you look at that way, the size of roughness elements according to the length scale will maintain the same resistance meter per meter L as long as the Reynolds numbers, the grain Reynolds number is greater than the 70s for both the models and the prototypes. This is the possible only very coarse bed materials are put it on the bed streams. Okay. The basically here you can have a fine sand to represent that, here put it either the boulders to obtain the, this is the model to obtain the same resistance. So, you try to know it how to do the scaling when you try to look at the similitudes of this part. Okay. Now, if you look at how you need to do it, as I said it, we need to look at the as we discussed earlier, near bed conditions will be drastically changed, because laminar sublayer thickness in the hydraulic models is relatively too thick. Okay. Laminar sublayer thickness, okay, in the hydraulic models is relatively too things. That is the reason you require to scale down the laminar sublayer thickness ratios in terms of shear velocity ratio than the length ratio. So, I just to repeat it that when you try to make it the flow behavior what is happening at the river level in the same thing conditions you want to talk about near bed conditions at the what is happening at the flume level at the laboratory scales, what we need to look at what is the thickness of laminar sublayers. The laminar sublayer thickness in a laboratory scales is more thicker than the case of the laminar sublayers in a river. So, we need to do a scale downs, okay, of laminar sublayer thickness. Okay. So, if you look at that way, we need to have we cannot maintain exactly geometric similitudes. The length similitude require very small particles. The scale modeling produce very large laminar sublayer thickness in the model. What I am trying to do it, because I have been completing this course of these lectures, physical river models, it needs to have a lot of knowledge on the nearby bed conditions, what it happens in the river. The same conditions whether you can prevail or you can maintain with a ratio at the flume scale. That is the very challenging task. Like the same concept like hydraulic smooth regimes, resistance to flow increase as the Reynolds numbers decreases, the resistance to flow will be larger on the model than the prototype in case of hydraulic smooth regimes. So, we try to river knowledge, mechanics knowledge what we have, if you try to correlate it, you can see that when you do a scale down models, there is a issue on change of the laminar sublayers as well as the flow resistance. Okay. The exact simulation of near bed flow conditions cannot be preserved when the same fluid is used. Okay. You just try to understand it. Okay. The viscosity effect cannot be neglected. Exact simulation would require different fluid for the models and the prototypes. That means, the river may have the waters, but you can do other materials where you can satisfy this the flow resistance similitudes. Okay, that same ratio we can maintain it at the model levels and the compared to the prototype levels. Now, if you look it, we can develop the length ratios, okay, considering the basic definitions of the fluid properties, flow properties. That is what is Queen can do it. If you look at this rigid bed, okay, exact one, tilted one, and complete general ones. Okay, that is 3 conditions. For a mobile bed, you can have a m equal to the Stickler coefficient m equal to 1/6, and you when you have a grain particle size ratio, that is what is not equal to 1 you will have, and you have incomplete. So, if you look at these tables, okay, which clearly indicates as that I can compute the geometric particle diameters, the cross sections areas, the volume, kinematic properties like time, the flow, at the bed, velocity, shear velocity, settling velocity, discharge, unit bed loads. Okay, QBR stands for unit bed loads, which is we consider for the mobile bed. And if you look at the next ones, the mass, the pressure, the shear stress, force, and the dimensional lessons number like slope, Darcy-Weisbach, FR values, Prof, Reynolds number, Silt numbers, grain Reynolds numbers, dimensional diameters. Okay, these types is a dimensional and the sediment densities. Okay, if you look at that, I just to encourage it, you have the self readings on these chapters to know it what is the scales and the exact and the tilted case. In case of the mobile bed, we have a general, we have a different conditions of dimensionless diameters and the incomplete part, which we are not discussing here. So, if you try to look at these things, we can derive it, and that is the modeling part. Now, I will be not going more details, but I just put it as empirical nature, but you try to derive it. When you do the Proud similitudes for tilted river models. So, we make a tilted river models where a YR length, the vertical ratio and the lateral ratios are not equals. In case of the tiltings, you will have a case of XR, the longitudinal directions ratio and the vertical direction that not acceptable. So, when vertical and lateral accelerations of water can be neglected with respect to them. So, basically it allows the different scale for flow depth and the sediment size. Again, you can look at when you have a the grain Reynolds numbers is greater than 70s, the resistance to flow depends upon relative submergence. That is what we discuss when you talking about the resistance. Okay. That way, if you look at how you have to have a 2 equations to satisfied here is the flow Proud numbers as well as the flow resistance equations. To satisfy both, we are writing the resistance equations in terms of flow Proud numbers here, as the flow Proud ratio is equal to 1 and you have a dxr is not equal to 1. From the resistance to flow, which is Darcy-Weisbach formulas, we can establish a x point component is a function of h by ds, the submerged ratios. Okay. That is what, and if you put it that equations, you will get it the flow Proud ratios are as a function of ZR, XR and DXR and exponent of 2m. This m, when you talk about Manning-Stickler's equations, this m is equal to 1 by 6. That is what if you remember the Manning-Stickler equations, we define the n is a function of dx to the power 1 by 6. That is the power exponent point which m equal to the 1 by 6. That the instead of we can use m equal to 1 by 6. So, in that case you will have the 3 criteria. Okay. Just try to understand. So, you have a 3 criteria. That means, it will be most will satisfy the Proud numbers, Manning-Stickler's simulators criteria. If you use all these equations, then you will get it in a distorted models, you will have a relationship like this. Okay. A tilted models, you will have a not equal to that, satisfy the Proud numbers, you will have a DXR relations. Now, if you look at for these equations, we have a 2 degree of freedoms, okay, selecting from 3 parameters XR, ZR and DXR. Okay. XR, ZR or DXR. So, we can consider that and change that value. Still the model and prototypes should satisfy these 2 conditions. Okay. As it follow that conditions, we can have a say that it is having the Proud and Manning-Stickler's similitude criteria. Now, if you look at this is what the notes is there for when you do the rigid boundary models. We have to look at that when you have a roughness is typically increased with a disproportionate large block of sticks are used to produce the state register relationship which are comparable to the prototypes. Okay, that is we have to do it. And most of the times, as it says that when you work with a distorted rigid border models, you need to have intuitions and judgment of experience, okay, of engineers. That how its matter is often encountered by engineering practice where the flow depth is increases, and that what is exact simulations. So, a distorted model with a different horizontal border allows the different scales for the bed materials and the forward depth. So, that is the point I can show for the rigid bed reborn models. In case of mobile bed reborn models, I just want you to go in depth because the course is already is 24-hour lecture is over. So, I am not going more detail about mobile bed models, how we develop it, but in a short I will tell you that this type of models are necessary when you have a sediment transport is a significance. That means, silt parameters greater than 0.06. Okay, that is the conditions which read that. That is what is necessary for the local scour, erosion below the spillway, locks, dams, reservoir sedimentations. For those studies, we should go for mobile bed because that what will be said. When you do these ones, what is there the similitude criteria is that Proud similitudes, resistance similitudes, that is Manning-Stickler formulas, dimensional grain diameters, bed material, entertainment and silt parameters. So, if you look at that, the 4 equations we have to satisfy it. The Proud similitudes, the resistance, that is what is Manning-Stickler formulas, dimensional less grain diameters, bed material, entertainment or the silt parameter. So, we need to satisfy all these 4 conditions. We have the different ratios. Okay. If you look at that velocity ratio, acceleration ratio, flow depth ratios and all, to make a complete mobile bed simulations, I am not going to more detailed derivations. I will say it, we need to do for a 1 degree of freedoms. Okay. 4 equation simulations are simultaneously to be satisfied. So, then if you look at the simulation dimensional parameter of diameters and the models is gives like this. So, many of the times we go for a different bed materials, like we to satisfy these conditions we cannot use the same bed materials. Okay. We go for different bed materials of a different specific gravity and the typical size. Okay. That will be the different values will come it, and you will have a comments about that. That means how the size variability is there and the specific, because then it can satisfy all these flow criteria, which will be giving a particle diameters, the ratios in terms of specific gravity. Okay. So, we can choose a specific gravity such as that this what can be satisfied with a typical pi size. So, that is the reasons it is many of the mobile bed models we use the different bed materials, not the sand or not the gravels, based on these studies what we do it. So, now if you look it, I am not going more details, but I will tell you that always it has to look at that what you are looking at. Like for examples, you are looking at sediment suspension based on the settling velocities. For a suspended load, you should look at the settling velocity component. If you are looking at silt parameters ratios, you can look at how you are to making this ratio equal to 1. So, those things what I am suggesting is that you can have a self readings, because as the this is one of the bridge models is considered way back in United States, that which is what collapsed in 87 with a discharge of this. This is what ZR ratios, vertical scales, time scales. Okay, sorry, this is velocity scale, the time scales, the discharge scales, and try to look at the Hertz vortex near the base bridge pairs, and that is what is the instrumentations happen it and the hundreds. So, as we discussed earlier much details about this. So, that is what is done it to know it why the bridge is collapsed on this date, and that what is gives us design guidelines or for constructing a pier in a river. So, that is the points is there. Now, if you look at just a one examples, I will show it here, that other examples you can have self studies. So, if you look at that, consider model of large sand which is flow depth of 8 meters, velocity 2 meter per second, slope is there, y and zr ratio is there, then discharge is there. So, first you have to compute the silt parameters. As the silt parameter is more than 1.7, then we need to know consider is mobile bed. Okay. Then we need to compute the m value. Okay. We can compute this m value, and based on that tables what I showed it to you, we can compute it the ratio in downstream distance, model particle diameters. We can because we know the prototypes 0.2 mm is there, and you can compute it what will be the model particle diameters, the time scale of bed. That is what you can compute it for a time scale for bed and time scale for this component. You can compute it, and once you compute this part, then you can go for velocity ratio. Okay. From the velocity ratio, as we can compute it what will be the model velocities, we know the QR values, we can get the model discharge, we can get the model slope, we can get the model density. Okay. Sediment densities functions we can get it. Okay. And which is coming about to be g equal to 1 point, which is lower than the density of polyesters. So, a incomplete model will be unfortunately by indicated by these model scales. So, if you look at that, when you get this model sediment density, it is clearly saying to us that we cannot use these present materials, bed materials, alternative bed materials. To do it, we have to go for incomplete mobile bed models. The second example is quite interesting examples, like that is a clear water open channel model. The maximum laboratory discharge is given to us. Okay. The maximum laboratory discharge is given to us, which is a 4 liters per second. The stream discharge is 300 meter cube per seconds. The laboratory allow the maximum length of 60 meters to model the river of the 10 kilometers. Okay. Determine the suitable scaling length for model, determine the scaling ratio for the time, discharge and the hydropowers. So, if you look at these models, that means we have to have a Proud numbers similitudes. Okay. So, we need to make the Proud numbers of the models is equal to the Proud numbers of prototypes. So, if that is the conditions, that is what we are substituting here. Since GR equal to 1, okay, GR equal to the accelerations ratio of the accelerations is equal to 1. So, we can rewrite it, and you can rewrite in terms of velocity ratio and the length ratios. And if you look at next component is that because there is a constraint only 60 meters we can use for the 10 kilometers, we have the length ratio. Okay, that is a fixed for us. So, we can compute the discharge ratios to have a how much of water is necessary. For that is 0.8 liter per second, which is much lesser than 4 liters. So, that means we can provide a scaling length of 60 meter, which could require discharge of 0.8 liter per second. So, this is what the design of a physical models. We do it based on the conditions what we have in our plume, and what is the prototype size, the flow variabilities range, and what we are trying to do it. That is whether the mobile bed, whether the rigid bed, or only flow Proud similitudes, or we are looking for the resistance simulations. So, with this I need to look at that again you can have a time ratios, discharge ratios, and this hydropower ratios part you can put it to get it what will be the values what you are getting it. Okay. Now, let me I complete this course as well as this class looking at that physical river models actually gives a confidence to a field engineers before implementing any mega projects, because as you know it, most of the river projects are very costly. So, it is not easy to modify it, okay, if you do a mistakes. That is the reasons it gives a lot of confidence to the field or the hydraulic engineers before implementing the project. So, most of the big projects, as I said it, the Kosi barrage project or whatever the project implement in our country, we always do a physical river models in central water power research stations in Pune or other places. So, physical river models are the major components any mega projects when you implement it. Because when you try to make a guidelines for river training works or river infrastructures, we should have the physical models which will be like a scour countermeasures, the ecological study. Today we are talking about environment friendly hydropower projects. All these projects, if you want to do it, that we cannot do it only mathematical models, which cannot give a feel good confidence levels for hydraulic engineers or this technocrats to implement that projects. So, we need to have these physical model setups to give a confidence, and it can be a complementary with a mathematical river models. We have a recent technical challenge for the fluvial systems and the river ecology systems, river health, all are bigger issues. The combinations of mathematical models and the physical models can give us a set of the solutions which we can implement it. So, with this note, let me I finish these lectures by thanking all my research scholars who has done who has put a lot of efforts for you to prepare a good photographs from Chandan Pradhan's, Ketan Nandi, Ridik Kakoti, Lasyamoy El Sau. So, all they put it a lot of effort for you, these PPTs to prepare in that. End of the day, let me I put it river or streams is a cycle of energy from sun to plants to insects to fish. It is a continuum broken only by humans, although leopards. So, with this let me complete these lectures. Thank you.